Today's lecture is about random processes in spectrum or in spectral characteristics. So we have seen the random processes in time domain, and now we look at them in the frequency domain. The outline of what we want to cover is the following. We'll start with a quick review of LTI, linear time invariant system, LTI systems, power spectral definition, power spectral density, PSD definition, properties of the PSD, bandwidth for the baseband and the passband random processes, noise as a random process. We look at white noise, band limited noise, and passband noise. 3 different examples. Okay, so basically we need a quick review of signals and systems. If we have a system, this system is characterized in time domain by its impulse response, h of t, and the input signal is x of t. The output would be y of t. In the frequency domain, we can use the transfer function h of t. The input signal is the Fourier transform h of f or omega. Sorry, that's x of omega. X of omega, and here we have h of omega, and the output will be y of omega. Okay, so how do we go from time to frequency? We use Fourier transform. That was possible because the signal we are dealing with is a deterministic signal. We can have a certain expression, we can find it in the Fourier transform table, or we can use the definition of Fourier transform. So x of t is capital X of omega are Fourier transform pair. Then we go from one to another using the following Fourier transform relation, where we multiply by exponential and we integrate. And we can also go back from frequency to time using the inverse Fourier transform relation. You can see that I am coloring the little differences here. If you're going to use omega, then there is a differential here factor you have to take care of. If you are using f, then 1 over 2 pi is not needed. This is something we know before, but now dealing with deterministic signal, we can sketch the magnitude and phase of the spectrum. We can talk about a certain signal. But when we go to the random processes, then we cannot just write expression for the input signal. There is no x of t or x of omega. We are going to make a few assumptions. We're going to deal with specific signals, which are the stationary, and then we'll make things simple. We said the most important characteristics is we look at the correlation of the input signal, and we're going to assume things to be stationary. And the question is, what will be the correlation at the output? That's in time. And then in frequency also, we want to have an equivalent to the autocorrelation function, which we'll see to be the power spectral density. So we do not need full PDF to find the power and to deal with the systems. We don't need, if it's a random signal, all what we need is the autocorrelation or the equivalent frequency domain terminology or alternative, which is the power spectral density. To sum up, in this slide, we explained that we don't have deterministic signals, and in time we're going to use the autocorrelation frequency. There is an equivalent quantity, which is the power spectral density. For the power spectral density and for the power density spectrum, the power density spectrum, which is in short PSD, to understand what it means, let's go back to Parsifal's theorem. Remember that Parsifal says we can find the power in time and in the frequency. If you recall the power, the definition of the power, it's nothing but the integration over time over the square of the signal. So if we have integration over time of the square of the signal. So we have integration from minus infinity to infinity x squared, or if you like, as a function of time. Then we divide by the time. So if we have a certain period, right? So we integrate from minus t to t, and that will give me the energy, but then we divide by time to make it the power. Okay, if the signal is not periodic, we need to take the limit, because sometimes we have to make sure that we covered all time. If it's periodic, we can take one period. If not, we have to cover all the time. Now what you see here is that instead of dealing with the time signal, we have replaced it with the expectation of the random process in time. So this is the definition of power. On the second side of the equation, we can see that we can also find the power by integrating over the equivalent Fourier transform of the signal. So here x of t now is replaced with x as function of omega. The subscript t to indicate that we have to transform a certain average time limited signal which is periodic with capital T as a period. So basically Parsifal says you can find the power in time or the power in frequency. Now if you look at the right hand integration, you will find that you get the power by integrating a certain quantity. This quantity now is defined to be the power density spectrum. It's a density, it's not direct power because you need to integrate to find the power. So let's have this definition. You can make it, we can put it inside the box because it's very important. What is the power spectral density? It is the expected value of x, of the transform of x squared over 2t. And then we take the limit. Now, if you want the power, all you need to do is you integrate that power spectral density. We'll have a factor of 1 over 2 pi. Again, this factor is needed because we are dealing with omega. Have we used f, this is not going to show up. Okay, so we have defined here the power density spectrum. We'll use that into some examples. Before we conclude just this slide, recall that the power is related to the time averages. So if your process is wide sense stationary, what we need to do is the time dependence will cancel out and we get x squared bar, or the average of the squared of the signal. As you can see here, this is the general form, and if you have wide sense stationary, the time factor will drop. First example. This example says find the power in the following random process x of t, given as a signal, a cosine signal with random phase. So a naught and omega naught are both constant, and the phase here, it's varying uniformly and from 0 to pi over 2. Usually we have seen this as minus pi to pi, but here we are limiting it from 0 to pi over 2. Now, if you want to find the power on this signal, then you can find the expected value of x of the random process squared, which is given as a direct substitution here. We just squared here, we squared a, squared the cosine. Using trigonometry now, cosine squared is half 1 plus double the angle. You can see here that we have doubling the angle. We're using the trigonometric property or identity to go from the first equality to the second, to go from here to here. We just expanded cosine squared. Now the first term is outside the expectation because there is no randomness here. In the second term, we have to integrate over theta because it's the only random quantity here, and it's PDF. Since we are varying from 0 to 2 pi and it's uniform, the area has to be 1. So this is 0 from 0 to pi over 2, and it's uniform, so it's constant. This constant has to be 2 over pi. This constant, so it doesn't look very much constant, it has to be constant. Okay, and this is the blue thing here that you can see in the equation. This is the PDF of theta. Integrating over that quantity, we concluded with the following expression. Now notice that because we have limited the value of theta, this is not wide sense stationary anymore. You can see that the t, which is shown in red color here, this t shows you that there is a time dependence, and this correlation is not stationary. If you want to find the power, of course, now all you have to do is you take the time average of this expectation because it's function of time. The average is not constant, or the power is not constant. So if you average over time, you integrate over the time, you divide by time, and that would be simply a squared over 2. If you exclude the integration, you get a squared over 2. If your signal, of course, is periodic, you can limit the integration over one period. This integration should have been t. This integration should have been t and minus t. Okay. Now, another way of doing the same thing using Parseval theorem, what we could have done, we could have find the Fourier transform of the random process, and then we find the square of that, which, because in Fourier transform we have a complex quantity, you can get the square by multiplying by the conjugate, and now we get the power spectral density, which is the expected value of x of the power spectral density. If you want to find the power, you integrate, and of course you should get the same quantity. I leave this as an exercise for you to try. So start by finding the Fourier transform of this, find its square, and then find the expected value over 2t, integrate over time, and you should get the same answer. Alright, you can leave a comment if you don't get the same answer below, or if you get the same answer. Now for the relationship between power spectrum and autocorrelation, we're going to summarize things here. Okay, the power spectral density is nothing but the Fourier transform of the correlation. Why the power spectral density is important, the one that we have defined before, it's nothing but the Fourier transform of the correlation. And of course, the way you get it, we are dealing, of course, with wide sense stationary. So if your signal is not wide sense stationary, or it's a function of time, then you take the time average, and that will be the Fourier transform and the inverse Fourier transform of the power spectral density. Okay, so this is the Fourier transform pair, the two forward and backward equations to go from time to frequency. And then, of course, we can come up with specific identity here for wide sense stationary. We can go from time dependence into the green autocorrelation, where it does not depend on time, and we get the Wiener-Knittchen relation, which says that autocorrelation and power spectral density and Fourier transform of each other. So remember, we started by defining the power spectral density from the power equation, but now we also know that it's nothing but the Fourier transform of the autocorrelation. Alright, here is the first example in terms of the relation. It says that given the autocorrelation, okay, then it says then find the power, find the PSD. We just mentioned it's the Fourier transform. Cosine in the frequency domain will give you 2 deltas scaled by pi. Don't get confused. Cosine 2 by f has a Fourier transform of 1/2 2 delta, let's say f naught, 2 delta f minus f naught, plus delta into f of f plus f naught. That's in f domain. If you want to go to the, if you're using omega, cosine omega naught, there's time here, t will be by times delta of omega minus omega naught plus delta of omega plus omega naught. So if you're using the omega domain, if you're using the omega variable, there is a by here. There is a by here. If you're using the f, there is a scale of 1/2. So this is why here we got a squared over 2 from the original expression, and then we get by multiplied by the deltas, which is the Fourier transform of the cosine. Right? So seeing this in the figure, the left curve here shows you the autocorrelation, which means that the relation goes positive, negative as function of time, and in the frequency domain we got 2 deltas. What's the advantage of looking at the frequency domain? This is important if you want to know whether this your random signal is going to go through a low pass filter or high pass filter. If I give you, for example, a filter, okay, let's use a darker color. If we have a filter here and we tell you that there is a low pass filter with cutoff frequency equal to 2 omega naught, is the random signal here going to pass or not? According to this frequency domain power spectral density, we can see that 2 omega naught is here, so we have no problem. Have this been omega naught over 2, then we get 0 almost outside. There is no signal at the output on the average. The second example is this. For the second example, it says given the autocorrelation function, okay, then find the power spectral density. Of course, we're going to assume that capital T is a positive quantity and A naught is just another positive quantity which is constant. Okay, if you want to find the Fourier transform of this, either you use the definition of the integration. Okay, so you start, because you have the absolute value, you can split your integration into two parts. So one part will be for the negative part from minus t, okay, from minus t to 0. Okay, the absolute value will give you minus, so minus by minus you get plus. For the second integral, it will remain minus because tau is already, or we're integrating over a positive quantity. So the absolute value will just disappear. You can execute the integration, or you can go back to Fourier transform tables. In short, you're going to get sinc squared. Remember from our Fourier transform table, and this is how the autocorrelation look like on the left hand side. It's the triangle function, and its Fourier transform is sinc square. The rect function has sinc. Triangle come from convolution of two rects, which give you sinc square. Convolution in time give you product and frequency. So anyhow, just to make it simple, we got the rect squared, or we got the Fourier transform of the rect from the Fourier transform table. The beauty about looking at the power spectral density, it shows you how much the power is distributed as function of frequency. Okay, and that's important for going through filters, low pass, high pass, or band pass, and understanding how the power is distributed among the frequencies. Okay, now we look at the properties of the power spectral density. For any power spectral density, okay, we have to note that first thing, it's always a positive quantity. There is no negative power here, and it's an even function. Okay, for any real signal. So if you sketch the power spectral density, it has got to be, it's a Fourier transform of a real signal, so it has to be even. Okay, and we're looking at the power, so it's always real. It's not like Fourier transform in general could be complex, but here we're going to get a real signal. Okay, here is the definition of the Fourier transform. You can get the autocorrelation from frequency, from the power spectral density. Okay, and also this is one like a byproduct. If you have the derivative of the signal, then if you differentiate your random process, you will find out that the power spectral density will be the same but scaled by omega square. Why? Remember that in the power we have a squared, we are multiplying x by x basically, and differentiation in frequency is multiplying by j omega. So scaling by j omega, taking the absolute value, give you omega squared. So if somebody give you a random process, and you know it's and you got the power spectral density, and now we say what is the power spectral density of the derivative, then it's just the same multiplied by omega squared. All right, so now the power spectral density and time averages of the autocorrelation form a Fourier transform pair. We mentioned this a couple of times. We're using the general definition of autocorrelation. It does not have to be stationary, and in that case you have to take the time average going backward and forward. If it's White-Cell stationary, then of course you can simplify, you can avoid the time averages, you just use tau. Okay, these are a list of properties, and usually you have to be careful about number one. For a valid PSD, it has to be positive, and it has to be even, it has to be real. Otherwise, it's not valid PSD. Okay. Now, practice problems. Determine which of the following functions can and cannot be valid power density spectrum. For those that are not, explain why. So look at these now. The first one, the second one, and the third one. Is it valid or not, and why? Okay, so please leave your answers down. A, B, C, and D. You can freeze the video and think about it. Please leave your answers down. So just they have to be, remember, they have to be positive, even, and real. Okay, for the second problem, it says a random process has the autocorrelation function given by the following. All right, where B, omega naught, and W are positive constants. Find and sketch the power spectral density of x of t. This is basically Fourier transform. Compute the average power in the low pass part of the power spectrum. Repeat for band pass case. In each case, assume omega naught to be much greater than W. Alright, for this I'm sharing the answer with you here. I'm just going to go over this quickly, but I'm sharing with you a few things that you need to be able to answer here. This is the Fourier transform you will need, and the property of the frequency shifting, and the integration. This is needed to solve the problem. You can freeze the video again and solve this. Here is a quick go over the answer. Now the solution is basically that we would like to find the Fourier transform of the following expression. Okay. Now we will start by using some identities, because we have few pairs given, and cosine square is not there. There is exponential. So we can think of converting cosine square into 1/2 plus cosine into 1/2 times 1 plus cosine double the angle, as we can see here. And then cosine can be converted into exponential using Euler identity. Remember that we have cosine. Sorry, we can write cosine theta as exponential to the j theta plus e to the minus j theta divided by 2. This is how we go from here to the next inequality, or to the next equality. Now we are ready now. We have the cosine square simplified multiplied by exponential, so we're going to use this identity. And then for the one that has shift, that has exponential, there will be a shift. To do it in short, we are going to get the following pair. You can take your time to think about it. Okay, so the power spectral density is given by the following: B times W, and then divide by omega squared plus omega squared, W squared plus omega squared, and then we have two different expressions, similar but with a shift. Okay, now you can think of this as a low pass component. The one that starts at low frequency is low pass component, and this one that has shift in frequency as high pass component. If you want to visualize this, I'm sketching these expressions. Of course, we have to assume that this omega naught is much greater than W, and this is maybe given in the question. Otherwise, these three parts are going to overlap with each other. So we can call this the low pass part of the signal, the red part, okay? While the other parts you can think of as being the low pass part of the signal. Okay, so we are done with, I think, with the first part, which is finding the power spectral density. Then we can think about the high pass and the low pass. For the low pass, we simply mean the red part of the signal. If you want the power, then we integrate only the first expression, okay, over all frequencies. and we got the expression to be B over 2. So the power in low pass equal to 2 over B multiplied by or integration of the signal. For the second part, for the high pass, again we integrate over all possible frequencies, and then we have the following expression. So we got this is supposed to be 2 by here. Okay, so now I think we're good to go, and the answer to this is now B over 2. So the power turns out to be P over 2 in both cases, where B is, remember that P was the original amplitude or scale of the autocorrelation. So in this case, in this specific example, the power in the low pass equal to the power in the high pass.